Section 17.3 introduces titrations of strong acids and strong bases. Now you've already encountered titrations in the vitamin C lab in 1225, so you hopefully understand the idea behind it, but we're going to go through it anyway. And I want to point out that manual titration with a glass burette and a scientist turning the knob by hand is actually the gold standard for analytical determination of concentrations. You can use like electrochemical probes or spectroscopy to get a pretty good idea of the concentration of something. But if you really want 4 significant figures of precision in that concentration, then a manual titration is really the best way to go. So they're certainly still very relevant and practical in the world today. So the idea, when you do a titration, you have an analyte. And this is a substance whose concentration is unknown. And then you have a titrant. And that titrant is something whose concentration you do know. It's carefully standardized, and it will react with the analyte. And usually you'll have the analyte in like an Erlenmeyer flask, and then the titrant is in the burette being added slowly to the analyte. But in reality, you could put titrant in the flask and analyte in the burette. You could do it a little backward. In fact, that's kind of what we did when we standardized the the thiosulfate solution in the Chem 1225 lab, Part A. But anyway, the idea is you have some way of identifying the stoichiometric point where you've got equal moles of analyte and titrant present, and you add the titrant slowly until you reach that point. Well, this will make a bit more sense if we show you some figures of what it really looks like. Now, 17.3 is a video that you can watch on your textbook, but I wanted to include it here because this shows someone titrating by hand, and in the flask down here, it's colorless right now. There will be a color indicator which causes the solution in that flask to change color dramatically and suddenly once the titration is completed. And we'll actually learn more about those color indicators in section 17.5. Another way you could perform a titration is by taking electrochemical measurements. So if you have a pH electrode, then it can measure the pH several times a second. And ideally you would have that then connected to a computer to log the data. And you could do some analysis in Excel or some other spreadsheet program after the fact. You can titrate an acid-base reaction, a redox reaction, even a precipitation reaction, but acid-base is by far the most common in chemistry classes, and then redox is the next most common. You can titrate any reaction where you're able to somehow detect the concentration of titrant added or detect some other side reaction which is governed by those concentrations in order to detect what's called an endpoint. And I'm going to go a little bit out of order compared to your textbook, and I'm going to jump ahead and talk about what the equivalence or the endpoint is. So the endpoint is the point at which you actually stop your titration. So again, in a couple sections when we talk about indicators, it will become important why The endpoint is a distinct thing, why we talk about endpoints. The equivalence point is a theoretical point where where you have equal moles of your analyte and your titrant. And so a good way to, and the equivalence point is a theoretical point. You're never going to get the equivalence point exactly, if only because, like, if the slowest you can go is adding drop by drop, well, a drop is still pretty big in terms of chemistry. And so one drop will be too few and the next drop will be too far. And you can't really hit the equivalence point like perfectly, precisely, exactly. So the end point is where you actually stop. The equivalence point is this sort of ideal theoretical. And so if my my moles of analyte that I started with is equal to the moles of titrant added. That is the definition of our equivalence point. Well, how can we express the moles of the analyte? Well, that would be the concentration of the analyte times the volume of the analyte. And the concentration of the analyte, this is our unknown. We do not know the concentration of that analyte. But usually in a titration, you'll use a volumetric pipette to deliver a very precise volume of that analyte, so we do know the volume. And what's going to be the moles of titrant added? Well, that would be the concentration of the titrant times the volume of titrant that you have added at the equivalence point. So I'll call that VEQ. That's the equivalent point volume, because you're adding the titrant slowly, one drop at a time. So the volume we care about is the volume where we're at equivalence. So this formula right here, if you carefully measure the concentration of your titrant and you add it slowly and carefully so you know the volume at equivalence, and you carefully started with a measured volume of analyte at the beginning, then it's pretty simple math to solve for that concentration of the analyte. Okay, so let's show you some figures. With this would be a strong acid being titrated with a strong base. And so you see we're measuring the pH along the y-axis. The left axis shows you the, the volume of base that has been added in milliliters. And the pH is going to follow this characteristic titration curve where it starts out with the pH rising relatively slowly, and then suddenly the pH will leap upward, and then it will taper off and asymptotically approach the pH of your strong base titrant. So let's walk through these regions. As far as point A, the pH will be the pH of your analyte solution. And if you have a strong acid, then that's just the negative log of your strong acid's concentration. And in the case of a strong acid, you could get at least a couple of sig figs worth of a guess of what the concentration is just by measuring the pH at point A. But performing the full titration will give you better precision. You'll get more sig figs. Now, in the region B, the pH is going to be increasing because as you add base, that is going to consume some amount of your strong acid. And so your acid concentration will be going down. And if we think about how much we can expect the pH to be changing, well, over the course of this titration, if I decrease my strong acid concentration to 1/10 of its original value, then that should move you by 1 pH unit. And so you can be 90% of the way to your equivalence point, and your pH will only have changed by about 1 pH unit. Just thinking through the math of that. If your pH is equal to the negative log of your acid concentration, then you can get that acid concentration to 1/10 of its original value, and the pH unit should have increased by just 1 pH unit. But in this last little bit, here at C, that's when you have reached equivalence, and you've added exactly the same amount of base as you started with strong acid, and they have perfectly neutralized each other. And so the pH at point C should be precisely 7. And you can see in order to jump all the way up to 7, those last few drops of base added are going to cause a very sharp increase in the pH. And then here, part D and beyond, what you have here is you've continued to add strong base past the point of neutralization. And so the pH is going to increase until it asymptotically approaches the pH of your strong base titrant. And we have similar sorts of arguments for why the region immediately after C is going to climb so sharply. There is a very big difference between truly neutral water and neutral water that's had even just a drop of strong base added to it. And then that strong base will slowly approach the value for the titrant itself. Okay. So you've, hold up. The next figure, sorry, I almost forgot to show you. Figure 17.7 shows kind of the inverse. You can have a strong base as an analyte, and then you add strong acid as a titrant. And here we'll have basically the same idea in reverse. Point A will be the pH of your unknown strong base, and it can give you about a 2 sig fig estimation for the strong base's concentration. Along part B here, the pH will drop as you add your strong acid and reduce the concentration of that base. And then at C, you'll have a sudden drop to pH of 7, because that is where you have truly neutral water, where you have added precisely equal amounts of acid and base. And then beyond C, now you've added an excess amount of acid, and so the pH will rapidly drop down to the acidic range and then asymptotically approach the pH of your titrant itself. Now, we actually have what I consider to be a pretty substantial quiz related to titration of strong acids and bases. So even though this is an important topic, I think I'm going to defer to the quiz video to show you how to really deal with solving titration type problems. And we're also going to be looking at titrations of weak acids and bases in the next section, which will reinforce these ideas and introduce a little complexity. So I don't think it's too valuable to dwell too much on this. Let's go ahead and move on to section 17.4.